Okay, so for today's video, we're going to talk about how to get the resultant vector using the component method. Okay, so unlike your graphical method, this component method, the component method of getting the resultant vector, it would require you to first find the x and y components of your vectors before you get the result. Okay, so for this particular example, you're given with three vectors. You have the first vector is 20 Newton at 90 degrees, second is 30 Newton at 120 degrees, and the third one you have 25 Newton at 225 degrees. Okay, some of the, for the convenience of this answering this example, we would assume that all of the angles, this one 90 degrees, 120 degrees, and 225 degrees are being measured from a certain from same origin. So let's say that origin is your positive y-axis. So let's say this is 0 degrees, and this one is 90 degrees. Okay, see 0, 90. This one is 180, and this one is 270. Okay. So this particular angles that we labeled in your Cartesian plane will be your guide in determining where your vector would fall into the Cartesian plane. So let's locate the first one. So first one you have here 20 Newton at 90 degrees. So this is 0, 90. So most probably your first vector would fall in this direction, in this axis. So let's label it as F1. So next, your F2. Let's say this is your F1. This is your F2. This is your F3. Okay, so the angle given for your second vector is 120 degrees. So 120 degrees. So it is in between 180 and 90. So let's say this one, this is your F2. Again, we did not measure the angle accurately for this one, since later on we will just find the correct angle using the calculation for the components. So the third one is 225. So most probably in this one, between 180 and 270. So this one, this is your F3. Okay, so that is where your vectors will be located in your Cartesian plane. Okay, so next step that we're going to do for us to find the resultant is we're going to find the components of each of the given vectors. So for this one, we're going to use a table so that we'll be able to tally to record the components correctly. Okay, so in determining the x and y components, we're going to use the identity of a right triangle. So we're going to use the functions sine and cosine, and later on tangent. So for just a review, we're going to use this this phrases, so ka toa. Okay, just for us to be reminded of what function that we're going to use later on. So S is sine, that is opposite over adjacent. C is cosine, that is adjacent over hypotenuse, and tangent is opposite over the adjacent. Okay, so again, in finding the resultant vector, we're going to use a table. So the table that we're going to use is this one. You have here your F1, F2, and F3, and you have your x and y component for this. Okay, so in determining the x and y component, again, we'll be using the identity of the angle, or the right triangle, I mean. So meaning we're going to look for a way wherein we will be able to locate or determine what side of the triangle your x and y components belong. So let's start with your F1. Okay, So for f1, it is exactly in the x-axis. So when we say, or when we determine a particular vector that is exactly in a x-axis or y-axis, that means that all of the components of that particular vector lies directly on that particular axis. So for this one, you have your f1 in x-axis. So meaning, all of the magnitude of your vector is in x-axis. So your x-axis is 20 Newton. So nothing is left for your y-axis because all of the components of your first vector lies in your x-axis. So since nothing is left, the y component for this one is 0. Okay. So for the next vector, you have here your f2. So your f2, this one. So for your f2, again, we're going to use the identity of a right triangle. So we're going to look for a way wherein we can locate a right triangle from where the vector is located. So if you're going to use your x-axis as one side of your triangle, and then this one, this side, you'll be able to find a right triangle. By the way, the angle that we're going to use for this one, since the given is 120, and then the side of the triangle started from 90 up until the given vector, so 90 up until 120, the angle from this side to this side is equivalent to 30 degrees. So this 30 degrees, this particular angle, this is the one that we're going to use to find the x and y component of your f2. So again, x component, this one, this is your x-axis. Y, this is your y component, this is your y-axis. So if you're going to use this angle and you're going to find the x component, this one, this is the x-axis. So the x component of your second vector should lie here. So from this angle, the x-axis is adjacent. So if we are given with adjacent, and then this one, this is the hypotenuse, we'll be using the function cosine. The angle is 30 degrees, and the given magnitude is 30 Newton. So that is how we calculate the x component of your second vector. For the y component, so this is your y-axis, this one. So if you're going to move your y-axis, supposedly, your y-axis is in line with the opposite side of your angle 30. Again, this is your angle 30. Opposite side of your angle 30 that is in line with your y-axis. So we're going to use, since this is your opposite and this is your hypotenuse, we're going to use sine, opposite over the hypotenuse. So that is sine 30, and the given magnitude for your second vector is 30 Newton. So the third one, we're going to do the same. We're going to do the same procedure. We're going to locate the angle that we're going to use, and then from the angle that we can use, we're going to identify if your x and y axis lie in the opposite or the adjacent side. Okay, so this one, supposedly this is 225 degrees, but then that is from this point up until this point. So this point up until your third vector, that is equivalent to 225 degrees. So again, we're going to use the identity of the triangle. So we're going to look for ways wherein we would see a triangle where your third vector lies. So this one, that is a right triangle. So the angle that we can use for us to find the x and y component of your f1, again, that is between 180 to 225. So the difference between that one is 45. Okay. So we're going to use 45 degrees as the base or as the angle. So for this one, your x-axis, this one, again, this is your x-axis, and then if you're going to use 45 degrees to find the x component, and then if you move your x-axis, you would know that the opposite side of the angle is in line with the x-axis. So this one, that is the opposite of 45, and that is in line with your x-axis. So for this, we're going to use the function. Since it is opposite, so for your x component, we'll be using sine 45 degrees, and the magnitude is 25 Newton. So x is your opposite, so obviously your y is your adjacent. So we'll be using cosine 45, and that is 25 Newton multiplied by 25 Newton. Okay. So this is not yet the answer for the x and y component, since we need to get the value of your calculated x and y component. So 30 Newton cosine 30, that is equivalent to 25.98 Newton. So 30 Newton sine 30, that is equivalent to 15 Newton. So for your F3, 45 Newton multiplied by 25 Newton multiplied by sine 40, that is equivalent to 17.68 Newton. And cosine 45 multiplied by 25 Newton, that is also equivalent to 17.68 Newton. Okay, so we're going to add your x and y components for it to get the total. But then before adding the x and y components, we need to make sure that we give the correct sign for your x and y components. So we'll talk about sign, that the sign will be based on where your vectors lie in your Cartesian plane. So your F1 is in the positive x-axis, so meaning your x is positive. So it doesn't have any y component, so you don't have to worry about the sign for this one. So for your F2, that is here, this is your F2. That is it is located in the quadrant wherein x is positive and y is negative. So x is positive, then y is negative. So for your F3, this is negative y, this one negative y, and then this one, this side, that is negative x. So negative x and negative y. So we already have assigned the correct sign for your component x and y. Yeah, for your x and y components. So we're going to add now and get the total. So for your x, 25.98 minus 17.68 plus 20, that is equivalent to 28.3 Newton. So your negative 15 minus 17.68, that is equivalent to negative 32.68 Newton. Okay, so we already have here the resultant. So this resultant x and y component will tell us what will be, or where would be your resultant vector be. So based on the resultant x and y component, you have positive x component for your resultant and negative y component for your resultant also. Okay, so if you're going to graph that one, so you have here, let's say this is your Cartesian plane. Again, your Cartesian plane, you have here positive y-axis, negative, this is positive x-axis, this is negative y-axis, and this is negative, and okay, negative y, negative x. this is positive x. Okay, so again you have here 28.5 Newton and positive 1, then negative 32.68. So in the Cartesian plane, your resultant is positive 28, so your resultant x component should be in the positive x-axis also. So that would be, it would look like this. Okay, so let's say that the equivalent for this one is 28.3 Newton. So since your y component is in the negative side, so it should be pointing downwards. So let's say that is 32.68. This is Newton. So the resultant, or the combination of your x and y component, would be this one. Okay, we don't know yet what is the magnitude for this one, but then since we're given with 28.3 Newton and 32.68 Newton for the x and y component, and we can observe that there is a right triangle given, or there is a right triangle that we can derive from the given x and y components, we can find this one. So this is the hypotenuse, so we can use the Pythagorean theorem in finding the magnitude for your resultant. So okay, so this one will be using c squared is equal to a squared plus b squared. So it's up to you. If you're going to use a as your x and b as your y, it won't have any much difference. Okay, so you already have your resultant components, x and y components, so we just need to get the magnitude of the resultant. So that is c squared. So your x would be, let's say your a is your x, that is 28.3 Newton squared plus 32.68 Newton squared. So I disregard the sign, because anyways when you square this one, this will give you positive value for your sides. Okay, so for us to get the cancel the square in the other side of the equation, we're going to get the square root. So c for this one would be 43.23 Newton. So this is the magnitude of your resultant vector. So this one, from this point up until this point, this will have 43.23 Newton magnitude. Okay, so this time, at this point, we already have the magnitude. Next is we're going to determine the direction, or where your resultant vector would lie in the Cartesian plane. So since we have here this one, the right triangle, so we can use this angle for us to find the location of your magnitude, resultant I mean. So from this angle, we don't know yet what is the angle, but then from this one, we know that this one is opposite the angle, this one is adjacent to the angle. So opposite and adjacent will be using tangent. Tangent theta is equal to opposite over adjacent. So opposite is 32.68 Newton over adjacent, which is 28.3 Newton. Actually, you can disregard the sign here, because the negative sign for this one is only directional. It only tells you that the y-axis is the y component is in the negative y-axis. But then with regards to the right triangle, Tangent is just, will just tell you how your opposite and adjacent side are connected to each other with regards to a given angle. So you can disregard, or you should disregard the sign for this one. So tangent theta, that 32.68 divided by 28.3, so you will have approximately 1.15 as the quotient. So you're going to look for the angle. So we're going to transpose your tangent. So that is arctan multiplied by 1.15. So in your calculator, what you're going to do is you just need to click shift tan, so that you will get the arctangent, or the second function sa iyong tangent. So the angle will be equivalent to 49.108 degrees. Okay, going back to our given example earlier, this one. So based on our given example, the angle is measured from your positive y-axis, and it has a given value of 0, this one 90, this one 180, and 270. So just for us to be consistent, we also need to describe the location or the angle of your resultant vector using this one, this pattern. So meaning, for your resultant, this should be this should be 0, 90 degrees, 180, and this one should be 270 degrees. Okay, again, okay, so again 0, 90, 180, and 270. Okay, so from this point, your resultant is in the second quadrant already. So it passed the 90-degree mark. So this one, and then this angle, this is equivalent to 49.108 degrees. So for us to to be consistent in describing the angle, we're going to consider this one, 0 to 90, and then 49.1. So we're just going to add 49.108 plus 90. So the resultant for this one, the resultant has a magnitude of 43.23 Newton, and the angle, again, just for us to be consistent with the givens, we're going to add 90, so that would be equivalent to 139.108 degrees. So that is from this point up until your resultant.